Hello, good evening, everyone. So the lesson for today is to work on two more tutorials rather quickly, and then I will prepare the one and remaining exercise. Actually, I'm just going to upload what I already have. I was making good progress, and then my web host, where I stored everything, decided to cancel my account 18 days early, and they have not responded to my email that showed that the thing was paid up through May 12th, and this is not May yet, and they disconnected everything. So I'm a little bit frustrated because of that. So I dug up what I could from other resources. And that's how it goes. So what we wanted to do today, or what I want to do, is not that one. Definitely not that one. Oh, I'm not even sharing my screen, so I guess you have no idea what I'm doing. That was a good move on my part. There we go. Now we have the screen all shared. I'm going to our lesson thing and go to Storm. And I want to get Storm tutorials 2 and 3. All right, how am I going to do this on my computer? I need to go there and then go to here. Make sure I don't have them already. Oh, it looks like I actually already have them downloaded. I'm pretty sure tutorial, just in case I'm wrong, let me just download. Save it in there. God, what part of? Nice. Okay, this is a confluence, so let me see. JPEG, that's all I want to say. I just need one image. Maybe that's right there. I can't tell. These are two different places. Okay, that's what I was afraid of. I'm embarrassed because I don't think I can actually figure out what my tutorial is. I will try this the hard way. I'm going to try to figure out what my tutorial 2 is. It's definitely not that. Oh, come on, don't tell me you're going to stop working now. Okay, number 2. Okay, we're going to attempt to look at the file names. R5 TPO. No thanks, just work. Quit being such a snotty computer.
Hi, Dr. Cleveland.
Hello.
Sadiq said he's in the waiting room, so you should let him in.
Thank you for telling me. Gotta figure out how to do that. There we go. So I don't know what my tutorial 2 is. Let me go back and see what I can get from, of course. Should be a topo file. Yeah, this is missing. Need a hex editor for that. I use their version. I can't recover my version of tutorial 2. So using their version, it's the Colorado River, and there's our data files. And who recalls how we get a storm model up and running? Easy question. Click on an icon on my desktop. Which one? IRIC. Yay. And I want to open a project, and now we're going to have to do some navigating. Go up to Storm, Tutorial Data, Storm, Tutorial 2. And naturally there is no project there because I'm being a dumbass. Okay, let me cancel that. Create a new project. Choose OK. Now we can start to get data. So let's open geographic data, and we're going to first try to find elevation. Now we go navigating through everything. Okay, so now the next thing I want to do is get an idea of what I've just mapped. So I'm going to attempt to get background images. See if I can do multiple. No, it would be too easy. Maybe a control. One at a time. That's very annoying. So we're now pasting together the images. We're going to end up turning them off, but let's get them loaded in anyway. 6, 7, 8, 9, 10, 11, 12. So assuming the georeferencing is correct, we've got this curved portion and there's no background images up here. And let's take a look at the example that we're using. So this is example 2. So that picture looks the same. Yay us. We put in some imagery. And let's zoom in just a touch more. Come on. I'm talking to my computer because it has decided to be disobedient. I'm guessing my hosting service is able to reach out and mess with my computer somehow. I'm going to turn off our elevation points. And so here's what we're going to be simulating. I guess the flow is coming from down here and working its way up this way. Now, the reason I'm making that guess is rivers deposit on the inside of the turn and the backside of obstructions. So there's a deposition there. Of course, there's one here too. We'll see what it tells us. But that's the area we are simulating. So let me turn my points back on. Let me turn off all my background images. Zoom back out. So I have a horseshoe. And our next important step is we're going to go ahead and save this. Save it as an iProject file. And now I want to use the same convention I did before. Okay, so I called one of my projects. So I'm going back to Storm Tutorial. And I'm going to create a new folder. In class. And the reason I didn't upload my project files from last class meeting, because I had intended to do that, is I realized the project file is metadata only. So it's pointers to where everything is. It would be of no use to you guys. Like, I suppose I could try to upload everything, but then you'd have to download it in the same directory structure I have. So yet another weakness of this fine, otherwise really cool software. So we're going to save it there, and we're going to call this my second tutorial. And it's going to be very much like last time. We'll go ahead and create a mesh, and basically I'm going to follow the tutorials, because what we're learning is trying to develop the necessary muscle memory to be able to operate this program. So we're going to, looks like we want to produce a section right about there. I have no idea where that is, so let me right in this region right here is where we're going to operate. So we'll create a grid from Polygon shape. I choose grid and then grid algorithm, press the okie dokie button, and now it's going to tell us, well, draw a picture, and then I'll do my thing. Let's see if I can edit that, because that's all messed up. Ah, that was close. You can use Mr. Hand here and move stuff around. Now I'm going to add a vertex. Okay, I'm getting a little bit artistic admittedly, but I want to be somewhat faithful to their Polygon. Okay, so we've done that, And I'm going to go ahead and save my work. And then the next thing, what was our next step from last time? While you're looking at your notes, I'm going to try to find mine because I had that sequence. Okay. We built the grid is our next thing. So we've created our polygon. We don't have anything about boundary conditions yet. Let's go ahead and create a grid. We can use some defaults. Let's zoom in a bit. That's actually a pretty coarse grid. We're going to go with that just to make today's lesson fast. Save our work. Done. Next step is to incorporate boundary conditions, and now I'll have to go back to the USGS provided tutorial because look at the grid they built. Do you want to do one as, no, we're going to do this real simplistic one I've done. I just need to figure out which way are the boundary conditions. Looks like inflow is up here. And you'll notice I'm departing somewhat from the USGS example. I'm just following my own sequence. The key thing is to not run a simulation until all the pieces are in place. So 700 cubic meters per second is the boundary condition, and it's along this line. Zoom in just a touch more. Okay, so boundary condition setting. We're going to add an inflow boundary, and okay, so now I have the same boundary condition in the USGS example, much different grid resolution. They have probably about twice as many cells as in my example. Next thing is our downstream boundary condition, which is 838.59. So we navigate to our downstream location. We'll add an outflow. Get a little bit ambitious with the outflow stage, 838.59. Okay, okay, save. Claims it's done. Now let's see what other things we have to put in. We built the grid, we put in the boundary conditions. Next thing we have to do is provide our friction information. So back up here, I think is where they did friction information. They used a roughness of 0.035. So we will do the same thing because we don't need to be creative just yet. So I'm kind of closely following our simulation region. It's okay if it's a little bigger or smaller. So now we have boundary conditions, our roughness, And the next thing we're going to need to do is map everything. So let's see, boundary conditions, friction model. Next step is attribute. So we go grid attribute mapping, execute. We want to map elevation, roughness. We'll leave everything else blank except for the boundary conditions. Press OK, and please wait. As Tom Petty and the Heartbreakers say, the waiting is the hardest part. Save our work. Next thing is to set up our simulation parameters. So that's under calculation conditions. We're going to take our initial conditions. We're going to set some uniform ones, and let's see what they are using the example that they've provided. At least I think they provided it. Oh, this one actually has water surface elevations provided independently. So let's cancel that. And we'll try to import some hydraulic data. It claims it has water elevation. And let's see if it does. Yeah, it lied. Classic USGS training. A little bit of a lie there. So they do not have water surface elevations. We're going to have to make our own up. R5 stage 25K ancillary. On just a whim, I wonder if my old tutorial 2 has that data. Does not. It's right there. I'm going to copy that to see if we can actually get the water surface elevation that way. So import hydraulic water elevation. And we'll go to tutorial 2 in class. It is refusing to acknowledge the existence of that data. That is really quite annoying. It seriously won't let me cut and paste. That's really funny. Try one more time and then I will stop. Otherwise, I'd be insane. Oh, this is a Windows thing, huh? Oh, how do you turn on this stupid file name extensions? Copy that. Paste it. Okay, so the data is now there. And actually there's these ones .anc which also exist. So it's kind of interesting why it won't let us bring in the data. See what we get in file. Open, import. See if we have all files. Now let's see what it looks like if we can even find it. Interesting, it never even opened it. Well, this software has changed a lot in the last couple of years. I guess too many people were using it, so they had to make it unusable. Grid shape, node attributes. Turn everything else off. That's really weird. It didn't actually, it did not import the data, yet I have data. We can open this with should be a text file. Notepad, LMNO. Nope, it's hex. Oh, never mind that. We also have these stage here, which are not showing up as importable data either. So let's turn everything back on and yeah, it's not very useful. Okay, let me exit and hopefully I saved after I did the roughness conditions. So we can look at the elevations of the bottom, and we will set up calculation conditions. Let's see. To get our starting value, we're up here, so it has a negative x component and a negative y component. I have no idea what they should be, so I'm just going to go -1, -1. And from a water surface elevation, I'm going to use 800 and something feet. What was the value that they gave us? We could try to look at that file, but we already know it's unreadable. 25K. Ah, nice. So 842 to 838. So let's choose 840 as our initial water surface elevation. try to figure out how to read that in later on. So uniform initial conditions. Take the defaults there. We use milliseconds for our first guess, and then I always do just a few 100 time steps. So the solution here is going to be meaningless in the sense we're not going to use it other than to verify that the program appears to run. And then general protection faults are there. Save and close, save it. And let's go ahead and attempt to run a simulation. And none of those scare me. So we can look at the useless output, and let's give ourselves velocity magnitude. Now it kind of makes sense. The velocity is high in the channel part, and it goes to 0 out here where everything is dry. We could look at water surface elevation. These numbers at 856, so this is clearly nowhere near a starting solution. Bed elevation. Is not sure I'm very comfortable with those numbers, but I guess that's what came out of it. Let's see what the shear stress is. Okay, that's me making sense. The shear stress is high in the channel part where it should be. Regular elevation, so we have a higher elevation on the outside of the turn than on the inside. And let's see if that makes sense from the picture. Higher elevation on our outside than our inside. It looks like there's a cliff right up here, so I buy that for $1. All right, so now we're ready to modify our settings, and let's see if we can get by with a bigger time step. Okay, so these that number's slowly getting smaller. That seems pretty stable. That one's slowly getting bigger. This is getting smaller. And this one's getting bigger. Let's see what happens if we run the simulation a little bit longer. And this will show you why last class I pre-did all the calculations to show them to you. So it's grinding away. The little teeny squirrels are grinding, and oh, I'm impressed. That was actually amazingly quick. Something must have broke. Let's go take a look at. Oh, so that was a equivalent time of 100 seconds. So there's no way we've hit our steady state yet. But for grins, let's just look at our velocity vectors. And we will make some adjustments. That I probably overdid it right there. And there is our initial flow field. And if we had time varying boundary conditions, obviously these arrows would change length and possibly direction at this end. Similarly at this end. But since I'm feeling frisky, I'm going to go ahead and go to 100,000 time steps. We'll plot every 1,000. We're doing this in hundredths of a second. So that'd be 1,000 seconds, which is 12 minutes. And the lesson there is that multidimensional simulations use an ungodly amount of computer time to simulate a very short period of real time. So all that's going to happen is numbers are going to come up. I'm hoping it doesn't crash, but we'll know in a few seconds. It'll wait to the second to the last iteration to fail, because that would be the maximum waste of the human being's time. And then we're going to go pull up number 3. Half done. Sweet. So it was at 1 times 10 to the 3. So things start to fail when this hits 1 times 10 to the 8th or 1 times 10 to the -8th, in that range. When they start to get that big or that small, the solver is fixing to fail. And unfortunately, it doesn't stop just before that happens. Although I don't understand, it could. That kind of logic could be built into it. So I'm going to modify this again. Okay, kept my, yeah, I'll go with that. No, but one those smaller. So there's my field. I'm going to turn off the grid, and I'm going to take advantage of this little time deal, and we're going to step 1 frame at a time. So that's 10 seconds. So it's not really a transient. We have not given transient solver information. It is just trying to get to equilibrium, just like you did on the homework assignment. And this stuff up here, I think, is an artifact of computation, because I find it hard to believe that there's water up there. And I don't think 1,000 seconds is quite enough time for it to have resolved its but let's keep track of flow depths. So blue is shallow, no water, and green and red is deep. That's not what I want to do. Let's run the simulator. Okay, so that, and we would run that out to a longer period until we have a steady solution, extract that solution, save it as something like this, so that we can, in theory, reload it. Now I'm going to try to load that information in. Bad move. Oh, shit. You say that a lot. Oh, that was on video too. I'll edit that out maybe. See what I had saved. Okay, that actually I had saved everything that I wanted to. And now I'm going to try to import initial conditions. Okay. import so the CGNS are the ones I actually want to get because that's a prior solution. X, Y, and Z. Piece of crap software. Okay, we're about to have a bit of an argument right here. Where is duplicate? Okay. It's not going to behave the way it used to. So that's going to take a little bit of reverse engineering. All right, the next cool thing I wanted to show is, let's see how long they simulated for. Is the Streamline dealy thing, but I need to get a decent solution run. So let me see how long they ran theirs for. They did 600,000. Oh, I'm going to regret that, but okay. I will let that run in the background while I talk a little bit, and we'll be, okay, hopefully it will not crash. I'm going to minimize that. See if I actually can zoom. Oh, I lost. Good, at least I kept some graphics while I am talking. We have on the output, we have the ability to have it plot streamlines for us, which is somewhat cool, and also has the ability to do particle tracking. We can lay particles out and watch them progress through the solution domain. But to do that, we got to wait till we have a solution. We're at almost 15% completion. So I will just let that do its thing. Maybe. Oh, now all of a sudden my virtual machine is not working right. I'm having a bad computer day. Perhaps you all have experienced that in your life at some point. I wonder if it's all these things I have open that's clobbering me. Let me go ahead and quit that. I don't need Outlook. Don't need that open. I need Firefox open. I don't need Word open. Don't need that open. Don't need that open. Be nice if it would follow instructions. Get rid of Teams. Okay, I think that's about all I can get away with getting rid of. See how we're going. Getting a lot of not responding all of a sudden, so my computer is doing the crash thing. That guy can go away. Yeah, keep that, keep that, keep that, keep that. It refuses to terminate. Microsoft. Come on, let me kill the process, damn it. You know, I had Dropbox installed on this. There we go. Now the hard one, try to kill that instance of Windows. I gotta find it first. Okay, that's the one I want to kill. Doesn't want to die. That should give me some resources back. We're about 70% complete. Let's see, 50, 75. It is not going to get done in a hurry, is it? Yay. All right, so we went to all that effort to be able to have that happen. I have a different grid than they use, but what I'm really interested in is not having it crash. Oh, he just croaked on me. I bet you didn't even have it saved. We might. It didn't save it. Okay, I'm not going to make you sit through all that again. Let's go ahead and just open a prior project, because there's enough in here to do that. Okay, so there was our 2D model. Let me zoom in on it a bit. And let me turn off the grid. There's our flow field, and that is not necessarily the easiest thing in the world to interpret. So first thing we can do is we can turn off our velocity field. We can turn on Streamlines, and nothing happens. Okay, so here's how we create streamlines. You can either enter coordinate values or do a mouse drag. We're going to do mouse drag, and nothing will happen because it doesn't want to work today. Okay, add, apply, okay. How come it won't let me do the 2 points? Specify 2 points. Particles start from points generated equally spaced between these 2 points. I want to use mouse drag. Let's remove point 2, point 1, add a point. There was a reason I delayed showing off this software till the end, because I must have known it wasn't going to behave. It's not letting me draw the streamlines. See if the particle thing is all working. Okay, my bad. Let me turn some stuff off. So you have to draw the line, and then you apply the condition, choose OK, and we can turn back on the grid shape, and nothing will happen because I don't have enough time for the particles to move. You can see it's starting to generate particle trackings, but this particular, I touched nothing, it just crashed again. Okay, I believe that is the computer god's way of telling me that we are done for tonight. What you can expect for a homework assignment, I'll show it to you, is this one. That's what the homework assignment will be. Green River, which we've done, and then I will provide rectangular channel information and that information, and see if you can simulate a rectangular channel, put in streamlines and plots, and I'll work on this with you on Wednesday, and that'll be your last assignment. Because the software isn't working the way it did a year ago, I'm obviously very confused. And we will have to reverse engineer it, but it does have some useful features. And I will demonstrate the pond and pond simulation, because that leverages the particle tracking very greatly as a way to see how detention ponds actually work from a water quality perspective. So that's on the plan for Wednesday. Sorry that the software was being disobedient for me today. And I'm sorry that my web hosting service canceled my account 12 days early. For what it's worth, I wasn't going to renew it anyway, but I was paid up until May 12th, and so I'm kind of angry about that. And I have an email and a receipt that says that. And so we will have a bit of a fight. They'll ultimately, well, actually it doesn't matter because I wasn't going to renew them anyway. But I kind of needed it for the last 12 days of the class. So with that, I will bid you all adieu for the evening, and Jawad for the morning. As soon as I have the video rendered, I will put it up to my YouTube account. So assuming that you know how to get there, you should be good to go. And I will put the problem statement and the files up before the next class meeting, so that all the necessary components will be there to do that simulation. All right, have a good evening, everybody.
Good night. Thank you, Dr. Cleveland.
Bye-bye.
Thank you.
Thank you, Dr. Cleveland.
All right, have a good day, Jawad.
Thank you, Dr. Cleveland.